This uncontrolled discharge in an industrial panel represents raw electrical energy. In occupational safety, protecting workers from these forces requires mastering the physics driving them, rather than simply memorizing regulations. For candidates pursuing the Associate Safety Professional and Certified Safety Professional board certifications, this technical mastery is a requirement. The examination blueprints demand exact knowledge of how these underlying principles apply to hazard control. We will progress from the base electrical variables through complex circuit mathematics, ultimately mapping these outputs to their exact physiological effects on the human body. From there, we apply these calculations to NFPA 70E. This is the definitive regulatory framework that translates theoretical physics into actionable workplace safety standards. Mastering these theoretical principles is the prerequisite. You cannot design or enforce life-saving administrative controls in the field until you understand the mechanics of the hazard. Electricity is governed by three primary variables. The first is voltage, measured in volts. Voltage is the potential difference, or the electrical pressure that drives a system. The second is current, measured in amperes. This is the actual flow rate of the electricity. In human exposure, current is the specific factor that determines the severity and lethality of a shock. This model demonstrates their relationship. Voltage acts as the pressure pushing the current, while the third variable, resistance, measured in ohms, acts as the physical restriction opposing that flow. This diagram now shifts into a series circuit configuration. Here, the current remains constant throughout a single unbroken loop. If one component fails, the entire circuit is broken. Now the diagram reshapes into a parallel circuit. The components span multiple independent branches. Total current is divided across these branches, but the voltage remains identical across all of them. We also classify electricity by its delivery method. Direct current, or DC, flows uniformly in a single direction. Alternating current, or AC, reverses its direction periodically and is the standard delivery method for utility power and industrial machinery. Predicting hazard vectors in an industrial facility requires first identifying exactly how the current is divided and routed through these specific circuit topologies. This whiteboard displays the primary formulas for direct current applications. Ohm's law states voltage equals current times resistance, while the power equation states power equals current times voltage. For alternating current, the equations change. You replace resistance with impedance, represented by the letter Z. Impedance accounts for the combined opposition to current flow in an AC system. The AC power formula requires the inclusion of the power factor, or PF. This variable represents the efficiency of the AC circuit, ranging from 0 to 1, and is required for accurate risk calculations. When assessing total load, resistors and inductors follow standard scaling rules. They are additive in a series circuit and calculate reciprocally in a parallel circuit. This comparative table identifies the inverse relationship of capacitors. While resistors and inductors are additive in series, capacitors operate on a reciprocal logic, calculating additively only when placed in parallel. Failing to correctly transpose these variables, particularly by neglecting the capacitor inversion or the AC power factor, guarantees a miscalculation of operational risk thresholds. The primary vector for electrical trauma is biological disruption. This disruption is driven by specific milliampere thresholds, with 1 milliampere being 1,000th of an ampere. This gauge measures the milliampere spectrum against human biology. The absolute baseline of human perception occurs at exactly 1 milliampere. At 5 milliamperes, the worker experiences a slight shock and the beginning of involuntary muscle movement. The let-go threshold occurs between 6 and 30 milliamperes.
Here, involuntary muscle contraction locks the worker's hands, physically trapping them on the energized conductor and preventing release. Between 50 and 100 milliamperes, the current triggers ventricular fibrillation. This disrupts the heart's rhythm, leading to respiratory paralysis and a high probability of death. This high-speed depiction shows an arc blast. Secondary hazards include internal thermal burns and explosions generating metal vaporizing heat and lung-collapsing pressure waves. Human lethality occurs at mere fractions of an ampere. Relying on standard equipment protections to prevent human injury is a fatal error in safety management. Physical guarding is the baseline engineering control. Any energized parts operating at 50 volts or more must be guarded by approved enclosures or elevated a minimum of 8 feet above the working surface. For overhead power lines, regulations require a 10-foot minimum distance for lines up to 50 kilovolts. For every 10 kilovolts above that, you must add 4 additional inches of clearance. Within standard circuitry, you must distinguish between the functions of circuit breakers and ground fault circuit interrupters, or GFCIs. This 3D cutaway shows a standard circuit breaker tripping. Breakers are designed solely to protect equipment and wiring infrastructure from massive overcurrent that could cause fires. This GFCI outlet is designed strictly to protect human life. It detects microleaks as small as 4 to 6 milliamperes and severs the connection in as little as 1/40th of a second. In construction settings where GFCIs are not used, the law requires a written Assured Equipment Grounding Conductor program. This must be managed by a designated competent person. Flexible cords introduce distinct risks. Never substitute them for fixed wiring. Never attach them to building surfaces or run them through structural holes. A safety professional must select controls based on the specific hazard target, use breakers to protect property, and GFCIs to protect human biology. This blueprint of an industrial electrical panel illustrates the boundaries defined by NFPA 70E. The standard translates electrical physics into manageable spatial zones to mitigate shock and arc flash. The innermost radius is the restricted approach boundary. Only qualified persons using specific PPE and insulated tools may enter this zone. The middle radius is the limited approach boundary. Unqualified persons may only enter this zone if they are escorted by a qualified person. The outermost radius is the arc flash boundary. This is the calculated distance where an unprotected worker would sustain a 1.2 calories per square centimeter second-degree burn during an arc fault. Under the regulations, a qualified person must have demonstrated skills and knowledge in the construction and operation of the equipment, alongside safety training to avoid the associated hazards. Facility safety requires shared responsibility. Host employers must provide system installation data to contract employers so they can perform the required hazard assessments. NFPA 70E compliance is the mechanism that transforms mathematical physics into enforceable, visually defined zones of protection on the facility floor. This reference matrix organizes the high-priority data. Note the required variables. Capacitors calculate reciprocally in series, and the AC power formula must include the power factor multiplier. The physiological hazard curve scales rapidly. Perception begins at 1 milliampere. The let-go threshold traps at 6. And ventricular fibrillation occurs at 50. Operational thresholds dictate facility design. Guard energized parts at 50 volts, maintain 10 feet of clearance from overhead lines, and verify the 5 milliampere trip point of GFCIs. Every control, from grounding programs to lockout-tagout training, shares a single ultimate goal: achieving and verifying an electrically safe work condition. Preventing fatalities in the field requires the ability to bridge theoretical electrical properties with rigid, uncompromising hazard control. Thank you for learning with QHSE Talks.